Hello guys, and welcome to another exam past question review, and we are looking at numerical integration. This time around we are going to learn how to use trapezoidal rule to evaluate definite integrals. Now the essence of numerical integration arises because so many a times there are some integral that you can't just evaluate analytically, but if you have an idea of some techniques like trapezoidal rule or Simpson's rule or rectangular rule, you could be able to use them to get an approximate value of the value of that integral. So let's see how to use trapezoidal rule to evaluate this integral. So the first thing that we need to know is, first of all, from the question, they ask us to use 10 intervals. Okay, so we need to get the size of our interval. The size of our interval, okay, is gotten by subtracting the limits of the integral and dividing it by the number of intervals that you want to deal with. So let me just generalize. If I'm given an integral j equal to the integral of a, b, okay, and f of x dx, and I want to use trapezoidal rule to evaluate this, I'm going to calculate my h as b minus a all over n. Then I'm going to now use this as the value of j. The value of j is going to be h over 2 into y naught plus yl plus 2 summation y orders. So this is the formula that you normally use to evaluate the approximate value of the integral. And as we dive deep into this particular examination question, I'm going to explain what it means. Let me just tell you what I'm trying to say. So g is h over 2, y naught is the first ordinate, yl is the last ordinate. Okay, so you have your first ordinate plus your last ordinate, then you now have plus 2 summation y orders. So you have y1 plus y2 plus y3 plus dot 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 plus yn minus 1. So that's what it means. Then if you can understand, so you're basically adding the first and the last value, then you're multiplying all the other values while you're adding them by 2. Is that okay? So your h is the interval size. So we are going to demonstrate with the integral. Let's say j is equal to the integral from 0 to 2. Then you now have sine 2x exponential minus 2x dx. This is what we want to evaluate, and we are given that n is equal to 10. So we can define h as 2 minus 0 divided by 10, which is going to give me 2 over 10, or steps of 0.2. That's my interval size. So with this, I'm going to prepare a table. So we're going to prepare a table like this. So this is how I'm going to prepare my table. I'm going to prepare the table to have the following columns. So the first column is going to be my I can call it, okay, I can call it here my index. So the index will always start from 0. Okay, you can start with 0, and you now have 1, 2, 3, 4. So you run from 0 to n. So index runs from 0 to n. Is that okay? From 0 to n. So 0, 1, 2, 3, 4. Then we have 5, 6, 7, 8, 9, and 10. Okay. So sorry about that. So that's my index. Then the next column is going to be labeled as x subscript n. Then finally the last column will be y subscript n. So y subscript n is actually going to be this particular value here, whatever is in the integral. In this case, whatever is in our integral, what we have is this over here. So we are going to use it like this. Sine 2xn. I'll just put an n to it, then exponential minus 2xn. Is that okay? So this is what we are going to be evaluating. So this is how we are going to step our x. Our x is also running from 0 to, our x runs from the lower limit of the integral to the upper limit of the integral. Okay, so our x runs in steps of h. So in steps of h. Is that okay? So the lower limit to the upper limit in steps of h. So what do I mean? So the lower limit of the integral is 0 and the upper limit of the integral is what? 2. So our h is what? 0.2. So we are going to count from 0 to 2 in steps of 0.2. So we're going to go like this. We have 0, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8, and 2.0. So we have now evaluated our x, okay? And now the final thing that is remaining is to evaluate yn. So yn will be, okay, for each xn, you just plug it into this formula and you solve it. So sometimes I see some people creating a separate column for sine 2x, then a separate column for exponential minus 2x, and finally they will now multiply the answers. Okay, this is how people in the old generation usually solved their problem. They will create for sine 2x, they will create separately for exponential 2x. The way you should solve it is everybody nowadays have access to scientific calculators. Okay, I have a small scientific calculator here. So this is how you should solve it. You should solve it directly. You don't need to create a separate column for sine 2x and a separate column for exponential minus 2x. You just need to solve everything at once because you have access to a scientific calculator, and this will reduce the error that will build up while you're approximating the value of this integral. So what do I mean? Okay, now, so we are going to go to the calculator, our scientific calculator, and we are going to try to inject this value into the scientific calculator directly, straightforward. So this is how you do it. So you can see sine 2 times something, then times exponential, okay, minus 2 times something. Okay, so we have keyed in this particular function into our scientific calculators, and with this we can now solve quickly. Okay, plugging in the values of this abscissa. So we have, this is ordinates and this is abscissa. Okay, so the x values are the abscissa and the y values are the ordinates. So we are going to be plugging in the values of x so that we can obtain the corresponding value of y. So when x is 0, what do we have? So when x is 0, and make sure that when you're doing this particular calculation, the mode of your calculator should be converted to radians. Okay, you don't want to be doing a calculation with sinusoidal functions mixed with exponentials and you're still putting it in degree mode. Convert it to radians. Okay, please make sure you take note of that. Everything should be in radians. So when we plug in 0 and we plug in 0, we can easily get 0 as the first case. So we'll just keep solving. Here is 0.2, then here is 0.2. We get 0.26103. 0.26103. I'm working with 5 decimal places. Then if I solve again for 0.4, we'll get 0.32233, 0.32233. Then for 0.6, we are going to get 0.28072, 8072. Then for 0.8, you're going to get 0.20181. So 0.20181. And for 1.0, what are we going to get? So let's find out. So for 1.0, we're going to get 0.12306. So we continue. For 1.2, what are we getting? You get 0.06127. Okay, 0.06127. The next one is 1.4. We'll have 0.02037. Then we have 1.6, which is going to evaluate to 0 minus 0.00238 minus 0.00238. Then we now have 1.8 for the next. Minus 0.01209. And finally 2.0. Minus 0.01386. Okay, so we've evaluated the ordinates for the various abscissa values. And finally, we just need to plug it into the formula. So we can now say our I is equal to, or our J, sorry, I use the symbol J. So let me stick with it. J is the integral from 0 to 2. And you have f of x, which is exponential minus 2x sine 2x dx, or sine 2x exponential minus 2x, which is going to be, according to our formula, we have h all over what? 2. Then we now have brackets. We have y naught plus y, the last value is y10. Okay, then we now have plus 2 summation orders. Okay, y orders. So what does this mean? So we have our j is equal to, okay, h is 0.2 divided by 2. Then y naught plus y10, that's the first value plus the last value, and plus 2 brackets. You now have your y1 plus your y2 plus dot 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 plus y8 plus y9. Is that okay? So this is what it's gonna be. All right, so we can evaluate j as 0.2 divided by 2 and brackets. Your y naught, the first value on the table is 0, so this is y naught, and y10 is the last value on the table, which is this one over here. So we have 0 then plus minus 0.01386. So the first value plus the last value plus 2 brackets. You're gonna sum from y1 to y9. So we're now going to add all these values together inside the bracket. So from here to here. Okay, so that is trapezoidal rule for you. Trapezoidal rule is that after you finish evaluating all your ordinates, you're going to add the first value and the last value, and you're now going to add all the values in between them, and you multiply them by 2. Is that okay? And you divide everything by h over 2 in the bracket. So let's see how that will go. So for the first value in the bracket, we have 0.26103. So we have 0.26103 plus the second value in the bracket is 0.32233. So I'm just going to put a plus dot dot dot, then plus the last value before we exit the bracket, which is this one over here, is negative 0.01209. okay, minus 0.01209. So okay, so what you just gonna do now is get your scientific calculator and plug in this expression and add everything accordingly. Is that okay? So on my scientific calculator, I'm going to create it like this: 0.2 divided by 2, then times, I'm gonna open a bracket. So the first value was 0, then plus the other value was the last value was 0.01386. Then we now have plus 2 times, open bracket, the sum of all other values in between. So we're going to be entering it one by one. So we're going to start with 0.26103 plus, we have 0.32233 plus, we have 0.28072. Okay, we now have plus 0.2018 81, and you now have plus, you have 0.12306, and you now have plus 0.06127, and you now have plus 0.02037, and plus we have something negative. Okay, so plus minus 0.00238, and I have plus minus the last one, which is 0.01209. So when we finished evaluating it, we got 0.249838 approximately. So we have 0.249838 as the value of our integral. So this is about trapezoidal rules. Let me just summarize everything that we've done since the beginning of the video. So to start trapezoidal rule, first of all, you need to know the formula, and this is the formula, okay, over here. Then you need to be able to obtain these parameters, your h, okay, and your ordinates. So you need to obtain your h and your ordinates. So this is the last value, or you can call it yn. Okay, let me just use n for consistency. So you should be able to obtain each and every one of them. So this is your y of x. Okay, so your y of x, you can actually evaluate your y by substituting the corresponding value of x. Remember, x moves from the lower limit of the integral to the upper limit of the integral in steps of h. So this is the lower limit of the integral, 0, and this is the upper limit of the integral, which is 2, and the steps is in steps of h. And how do you get h? Upper limit minus lower limit divided by the number of points we want you to work with. Is that okay? Or not the number of points, sorry, the number of intervals. Okay, the number of intervals. So you get h and you evaluate. And remember, when you're solving for y, there's no need to create a separate sine 2x and separate exponential 2x. Solve for sine 2x separately, solve for exponential minus 2x, then you now multiply two of them. Why do you have to do that when you have a scientific calculator that can easily calculate these two at once? So you just have to plug them in and solve, and finally put the results into your calculator, and this is what you get as your answer. So let me just show you something amazing about the trapezoidal rule for formula. It's amazing, but in terms of accuracy, the accuracy of the trapezoidal rule is actually lower than what we call Simpson's rule. So Simpson's rule helps us to attain accuracy much more faster. Okay, so and finally, the Simpson's rule is less accurate than the analytical method of solving this particular problem. Now, I know I have not introduced us to Simpson's rule, but I'm going to use the formula for Simpson's rule to still evaluate the value of this integral. Okay, I'm going to use Simpson's rule to evaluate the value of this integral. Let's say I prepared this table, okay, and I want to use Simpson's rule to find the value of my j. Okay, so j Simpson's. So the formula is going to be delta x over 3. So this is for Simpson's rule. So as usual, you have your first value plus last value. Okay, last value. So this is your yn, then plus you now have 4 times summation y odd plus 2 times summation y even. So this is the formula for Simpson's rule. So once you prepare your table, you could just easily use this formula. And in Simpson's rule, delta x is no other than the h you already know. So our h is 0.2, therefore delta x will be 0.2. So we already have all these values. So let's evaluate Simpson's rule. So what does it mean? Our j for Simpson's is going to be delta x over 3, which we already know as 0.2 over 3. So our y naught will be there, our yn will be there. Then we now have 4 into y odd, means your y1 plus your y3 plus your y. Okay, let me replace this with 10 so that we can see how it is clearly. So this is 10. So y5 plus y7 plus y9. Okay, then plus 2 into y even, you have y2 plus y4 plus dot 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 plus y8. Y8 will be the last value. Okay, so if you can evaluate this particular stuff, so y2 plus y4 plus y6 plus y8, I just did dot dot dots, okay, because of the space of my screen. Now this is just what Simpson's rule means with the same table. So let's see which one of them will be accurate or which one will be more accurate. Now I'm going to try to calculate Simpson's rule, okay, properly. So this is for Simpson's rule. You have 0.2 divided by 3, then times. So we have the first value is no other but from the table you have 0, and the last value is no other, okay, from the table you have minus 0.01386 minus 0.01386. okay, so the first value plus the last value, so plus 4 times all the what odd ordinates, all the odd ordinates. So all the odd ordinates are I have my y1. I'm going to use this ink for it. So my y1, y3, y7, sorry, y5, y7, and you now have y9. So I'm going to pick all these values and I'm going to plug them into the place where 4 is. So 4 times, so you have 0.206 103 plus 0.28072 plus the next one is 0.12306 plus we have 0.02037. Then you now have plus, we now have minus 0.01209 plus 0.01209. Okay, So this is all multiples, okay, that are going to enter for that the odd ordinates. Then the even ordinates will be multiplied by 2. Okay, so for the even ordinates, we're going to use another ink now. We're going to use green. So the even ordinates will be like this: 2, 4, 6, and 8 over here. So all these ones will be multiplied by 2. So on our scientific calculator, we are going to say plus 2 times, open the bracket, then you now have 0.32 okay, then plus 0.20181 plus the next one is 0.06127, 0.06127, then you now have plus finally minus 0.00238. Okay, so that's it. Plus equal to, so this is what we get, okay, with Simpson's rule 0.256304. So from Simpson's rule, we got our J Simpsons to be 0.256304. Okay, so we can see that this was the value with trapezoidal rule 0.249, then with Simpson's we have 0.256. Now between the trapezoidal and Simpson's, which of the following is closest to the accurate answer? The accurate answer can be found by analytical method, or if you know power series, you could find the power series expansion of sine 2x and the power series expansion of exponential minus 2x, multiply them together up to the first 5 terms. 5 terms is okay. Then you now evaluate the integral and you substitute the values, okay, and it will give you the answer. But look at this function. The secret is that some functions can be integrated. If you are good with integration, you know that this problem can be solved analytically. In fact, back then when I was playing around with some reduction formulas, I was able to establish that I was able to find a reduction formula for myself anytime I see any problem like exponential ax sine bx. I was able to find a formula for it. That's exponential ax divided by, sorry, when you integrate exponential ax sine bx dx, you're going to get exponential ax divided by a square plus b square, then into minus, you will have b cos bx, then plus a sine bx. Okay, so this is a reduction formula plus your constant of integration plus c. So if you evaluate exponential ax cos bx dx, you're going to get exponential ax all over a square plus b square, and you now have minus, okay, this time positive b sine bx plus a cos bx, something like this, and plus c. So these are reduction formulas for evaluating integrals of this form. So since this integral is analytical and we are given that in this question, so we are going to try to solve for the exact value of this integral. So we are concluding that the exact value of an integral from 0 to 2 exponential minus 2x sine, what do you have here, 2x dx, is going to be our definite integral from 0 to 2. We'll have our exponential minus 2 x all over a square, which is minus 2 square. A in this case is minus 2 and b in this case is actually what, 2 squared. Okay, so into, you now have minus b is minus 2, you now have cos 2x, then you now have plus a. Since a is minus 2, I can just change it to minus 2 sine 2x. Okay, So I'm going to evaluate this definite integral. Okay, so we're going to evaluate this definite integral and see the exact answer for this particular problem. And with that, we'll now have taken care of Simpson's rule and trapezoidal rule and all of that in just one video. So this is what we have from the previous set. So let's solve this definite integral. Now, when we solve this definite integral, we already use our reduction formula to arrive at this level. So it means that we are going to substitute all these things when x is 2, then subtract from when x is 0. So you have exponential minus 2 into 2 and divided by this is going to give you 4 plus 4, which is an 8. Is that okay? Then into, you now have minus 2 cos 2 times 2 is 4. Remember, we are starting with when x is 2, then minus 2 sine 2 times 2 is 4. Is that okay? Then we are going to subtract from when x is 0. So you now have exponential 2 times minus 2 times 0 is 0 divided by 8, then into minus 2 cos 0 minus 2 sine 0, something like this. So let's evaluate this and see what we're going to get. So I'm going to go to my scientific calculator. Remember, your scientific calculator should be put to radians. Radians, don't forget radians. So work with radians. Okay, only when you're dealing with Fourier series that you can work with degrees, but when you're working with normal calculations involving exponentials and sines, or exponentials and polynomials, and or trigonometrics and polynomials, or trigonometrics and exponentials, you should work with radians. Okay, there's a reason for that. So we are going to put in exponential like this, exponential minus 2 times 2, which is exponential minus 4, divided by 8. We now have times, the first bracket is minus 2 times cos 4, then minus, sorry, I've not done, minus 2 times sine 4. Okay, so we are going to subtract this from the same thing. This time around, we already know that exponential 0 is 1. So you have 1 over 8, then times, open bracket, you now have minus 2. So sine 0 is 0 even in radians, cos 0 is 1 even in radians. So the only thing in this bracket will be just minus 2. Is that okay? So when we evaluate, so this is what we get. So this is the exact value of this particular problem, 0.256458. So 0.256458. 256458. So this is the actual value. So J actual. So we now want to compare J trapezoidal with J Simpson's with J actual. So what did we get in 3 of these cases? So for this particular problem, if we trace it back, we discovered that our J trapezoidal, that's the first one, was 0.249838. Is that okay? So for J Simpson's, what do we get? We get 0.256304. Now, the actual value is 0.256458. That okay? So you can see that in terms of accuracy, the Simpson's rule of evaluating numerical integration is much more accurate than the trapezoidal method. The trapezoidal method suffers a lot of errors which are larger in magnitude compared to the Simpson's method. Okay, Simpson's method is very, very close. Like, has it been we were just working with 3 decimal places, you discover that the Simpson's method is exactly equal to the actual value. Okay, so Simpson's method suffers from little error. Now, there's another method called the rectangular method, and that method is pretty straightforward. Hopefully in another video we'll analyze a problem with rectangular method. But what I just wanted to do in this video is to introduce you to numerical integration, and I have come to the end of the video. That's introducing you to trapezoidal method and Simpson's method. These are easy, and you shouldn't skip this question. If you see it in an exam, you should rush to solve it. Okay, and you should take your time, be very careful, work with your scientific calculator very much, and be confident enough to solve it. So in the next video we're going to solve another problem with Simpson's rule, and I'm hoping that will be it for numerical integration. So thank you for watching. Please like this video, subscribe to my channel, share, hit the notification bell to stay updated on future videos. Okay, I'll see you next time.